To describe the moon in detail, we would need an overwhelming amount of information. Every crater has a precise location. Every impact has a size. Every region carries a chemical fingerprint shaped by billions of years of collisions, erosion, and cosmic exposure. Even with modern instruments, the numbers quickly grow from thousands to millions. And that is only a moon, one of the simplest objects in the cosmos. A planet demands far more. A star even more than that. Temperature gradients, internal layers, magnetic fields, nuclear reactions, and life cycles that unfold over millions or even billions of years all have to be accounted for. Now consider the most massive single objects known to exist. Black holes. Titans capable of tearing stars apart and reshaping entire galaxies. Intuition tells us they should require the most information of all, that their description should be impossibly complex. And yet, the opposite is true. A black hole can be fully described using just 3 numbers. Its mass, its electric charge, its spin. Nothing more is needed. How it formed, what collapsed to create it, whether it was born from a dying star or from countless mergers across cosmic time. All of that disappears from the description. Every atom, every structure, every memory of its past seems to be erased, reduced to 3 silent parameters. If that is true, then a terrifying question follows naturally. Where did all the information go? Trillions upon trillions of bits describing matter, energy, structure, and history. Swallowed, compressed, or hidden in ways we do not yet understand. How can the most extreme and violent objects in the universe appear so simple on the outside, and why does the universe allow something so complex to remember almost nothing at all? In almost every corner of the universe, objects carry a unique identity. 2 stars with the same mass still differ in temperature, composition, age, magnetic activity, and internal structure. 2 planets may share a size, yet tell completely different stories through their atmospheres and surfaces. Black holes are different. According to a fundamental result in general relativity, all black holes can be completely described by just 3 quantities: their mass, their electric charge, and their spin, the measure of how fast they rotate. This result is known as the black hole no-hair theorem. In simple terms, it states that once a black hole has formed and settled down, all other information about its origin is lost to the outside universe. The black hole has no distinguishing features beyond those 3 numbers. It does not matter whether the black hole was born from the collapse of a massive star, from the slow growth of matter over billions of years, or from repeated mergers of other black holes. Once the horizon forms, the details of that history no longer appear in any external measurement. 2 black holes separated by billions of light years could be observationally indistinguishable if their mass, charge, and spin are the same. From the outside, they would behave in exactly the same way. Their gravitational pull, their effect on nearby matter, their influence on light and space-time itself would be identical. This behavior is profoundly unlike anything else we know. Even the smallest asteroid carries scars of its past. Even a cloud of gas retains subtle clues about its formation. Yet black holes seem to erase every trace of individuality, reducing an almost infinite range of possible histories to just 3 numbers. It is as if the universe deliberately strips black holes of identity, as if complexity is allowed to fall in. but never allowed to leave a mark. If black holes truly forget everything except mass, charge, and spin, then a deeper question emerges. Does this erasure of identity violate a fundamental law of physics? Or does it reveal one we do not yet understand? At the heart of modern physics lies a rule that has never been broken. In quantum mechanics, information is not allowed to disappear. When a physical system evolves, its information may become scrambled, dispersed, or hidden in complex correlations, but it is never destroyed. This principle underpins everything from atomic physics to quantum computing. It is as fundamental as energy conservation. Black holes appear to challenge this rule. When matter falls into a black hole, it carries information with it. The arrangement of atoms, the quantum states of particles, the detailed structure of molecules, even the memories encoded in a physical brain are, at their deepest level, forms of information. Yet from the outside, none of this seems to survive. According to classical black hole physics, everything that crosses the horizon contributes only to the mass, charge, and spin of the black hole. A library and a lump of coal increase the black hole in exactly the same way if they share the same total energy. Their internal complexity leaves no visible trace. An encyclopedia filled with knowledge. A hard drive storing entire civilizations of data. A living being with memories and consciousness. All of it appears to be compressed into the same three numbers. This is not merely unsettling. It is a direct contradiction. General relativity tells us that black holes are perfect absorbers. Objects from which nothing can escape once the horizon is crossed. Quantum mechanics insists that information must always be preserved. Both theories are extraordinarily successful. Both have been tested with extreme precision. And yet here, they seem to disagree at the most fundamental level. This tension is known as the black hole information problem. It is not a technical detail or a philosophical curiosity. It is a fault line running through the foundations of physics itself. The question is no longer simply what exists inside a black hole. It is whether the information that falls in truly ceases to exist, or whether it survives in a form we have not yet learned how to recognize. If information cannot be destroyed, then where is it hiding? For a long time, black holes were thought of as dead objects. Cold, silent, featureless sinks where matter disappeared and nothing meaningful happened afterward. That picture began to crack in the early 1970s. Jakob Bekenstein was the first to suggest something radical. If black holes truly absorb matter and information, then they cannot be thermodynamically inert. They must possess entropy. Entropy is not a vague concept. In physics, it measures the number of internal arrangements a system can have while still appearing the same from the outside. A hot gas has high entropy because its atoms can be arranged in countless microscopic ways. A cold crystal has low entropy because its structure is tightly constrained. At first, the idea that a black hole could have entropy seemed absurd. What internal arrangements could possibly exist inside an object whose interior is hidden behind an event horizon? Then, Stephen Hawking made the idea precise. Through careful analysis, Hawking showed that a black hole's entropy is not proportional to its volume, as it would be for ordinary matter. Instead, it is proportional to the area of its event horizon, the surface that marks the point of no return. This result was shocking. It meant that when matter falls into a black hole, the entropy of the universe does not decrease. The horizon area grows. the total entropy increases. The second law of thermodynamics is saved. Black holes were no longer violations of fundamental physics. They were participants in it. But this solution came at a cost. If entropy measures the number of microscopic states of a system, then Hawking's result implies that those states are somehow associated with the surface of the black hole, not its interior. As matter falls in, the inside remains unobservable. Yet the entropy keeps increasing in a way that can be tracked from the outside. Black holes, once thought to be simple and dead, suddenly appeared to have a hidden richness. They behaved like thermodynamic objects with temperature and entropy, despite having no visible internal structure. And that raises a deeper mystery. If we cannot see inside a black hole, and if its entropy grows with surface area rather than volume, then what exactly is being counted? What does the entropy of a black hole measure, if not the matter and structure hidden within? The idea that black holes have entropy led to a consequence even more unsettling. If a black hole has entropy, then it must also have a temperature. In physics, temperature is not a metaphor. It is a measure of how a system exchanges energy with its surroundings. Objects with temperature radiate. They emit energy. They are never perfectly inert. Stephen Hawking realized that if black holes truly obey the laws of thermodynamics, then they cannot be completely black. Through a remarkable calculation that combined quantum mechanics with curved spacetime, Hawking showed that black holes emit radiation, not by ejecting matter from within, but through quantum effects near the event horizon itself. This faint glow is now known as Hawking radiation. The result carried a strange inversion of intuition. The larger a black hole is, the colder it becomes. The smaller it is, the hotter it burns. A stellar mass black hole is unimaginably cold. Supermassive giants like Ton 618 are colder still, with temperatures far below that of the cosmic microwave background that fills the universe. In that sense, they are colder than space itself. Yet the temperature is not zero. Over immense spans of time, black holes slowly lose energy through this radiation. As they radiate, they lose mass. As they lose mass, they become hotter. And as they become hotter, the radiation accelerates. Given enough time, measured in billions upon billions of years, a black hole will evaporate completely. This revelation transformed black holes from eternal prisons into temporary objects. They are not the final state of matter. They have lifetimes. But Hawking radiation carries a troubling feature. It has the character of thermal radiation. It depends only on the mass, charge, and spin of the black hole. It appears random, featureless, devoid of any imprint of what fell in. If a black hole forms from vast complexity and then evaporates into simple thermal radiation, the problem becomes unavoidable. When the black hole is gone, where does the information that created it go? At first, Stephen Hawking believed the conclusion was unavoidable. If black holes radiate away their mass through featureless thermal radiation, then the information that formed them must be lost forever. This was not a small claim. It struck at the very heart of quantum mechanics. In quantum theory, the evolution of a system is reversible at the deepest level. Given complete information about a system at one moment, the laws of physics allow its past and future to be reconstructed in principle. Permanent information loss is forbidden. Hawking's conclusion challenged this rule directly. It suggested that black holes introduce a fundamental randomness into the universe. That information can be destroyed. That the future cannot always be predicted from the past, even in principle. The implications were profound. If information can be lost, then quantum mechanics is incomplete. The mathematical structure that underlies modern physics, from particle theory to chemistry, would have to be revised. The universe itself would be fundamentally non-deterministic. For decades, this question divided the physics community. Some researchers argued that Hawking must be wrong, that information somehow escapes encoded within the radiation. Others accepted the loss, believing that gravity forces nature to abandon quantum certainty at extreme scales. The debate was intense and unresolved. Unlike many disputes in physics, there was no experiment that could settle it. Real black holes are distant. Their radiation is unimaginably faint. No laboratory can recreate the conditions needed to observe the full life cycle of a black hole. The information paradox became a purely theoretical battleground. Equations against equations. Principles against principles. And yet the stakes could not be higher. This problem is not just about black holes. It is about whether the universe preserves information at all, about whether reality is fundamentally knowable, about whether the laws of physics are consistent with themselves. If information truly disappears into black holes, then our deepest assumptions about causality and reality are wrong. But if information is not lost, then it must survive in a form that does not reside inside the black hole in any ordinary sense. So, where could it possibly be? The strange behavior of black hole entropy pointed physicists toward an idea that was once considered almost unthinkable. If entropy measures information, and if that entropy grows with surface area rather than volume, then information in a gravitational system may not live where we expect it to live. This was the birth of the holographic principle. The principle proposes something radically counterintuitive. All the information contained within a region of space can be fully encoded on the boundary that surrounds it. In other words, a three-dimensional world may be completely described by data written on a two-dimensional surface. For black holes, this surface is the event horizon. According to this view, everything that falls into a black hole is not stored deep inside its mysterious interior. Instead, the information is somehow imprinted on the horizon itself. The boundary becomes the bookkeeper of reality. This idea turns our intuition inside out. We are used to thinking that the interior of an object contains its substance, while the surface is merely a shell. The holographic principle suggests the opposite. The surface holds the fundamental information, while the interior emerges from it. What began as a clue from black hole thermodynamics soon grew into one of the most powerful ideas in modern physics. In the late 1990s, researchers discovered a precise mathematical realization of holography known as the anti-de Sitter conformal field theory correspondence. This result showed that a gravitational universe existing in a higher dimensional space can be exactly equivalent to a quantum theory with no gravity living on a lower dimensional boundary. Two theories that look completely different describe the same physics. In this picture, gravity is not a fundamental ingredient of reality. It is an emergent phenomenon, arising from the collective behavior of more basic quantum information encoded on a boundary. Black holes no longer destroy information. They reorganize it. The information paradox begins to soften. What falls into a black hole does not vanish. It is translated into a different language, stored not in the volume of space, but on its edge. If this principle is correct, then black holes are not exceptions to the laws of physics. They are the clearest windows into them. And the implication is staggering. If space-time itself can be described holographically, then what we experience as the interior of the universe may be a projection of deeper information written elsewhere. If the universe is a hologram, then what does it really mean to be inside anything at all? Beyond the event horizon lies a region of the universe that science cannot observe, cannot probe, and cannot report back from. No signal can cross the horizon and return. No light, no particle, no message of any kind. Once something passes that boundary, it is causally disconnected from the rest of the universe forever. Because of this, everything we say about the interior of a black hole is indirect. There are no measurements, no experiments, no observations, only mathematics. General relativity allows us to write equations that describe what space-time might look like inside the horizon. Those equations predict a dramatic fate. As matter falls inward, space-time curves more and more severely, until it reaches a point where the curvature becomes infinite. This point is known as a singularity. A singularity is not a physical object in the usual sense. It is a signal that the theory itself has failed. When quantities become infinite, the equations stop making meaningful predictions. Cause and effect lose their structure. Space and time cease to behave as concepts we understand. Rather than revealing what lies inside a black hole, the singularity tells us where our knowledge ends. Modern physics does not accept this quietly. The appearance of singularities strongly suggests that general relativity is incomplete. At extreme densities and energies, it must be replaced or extended by a deeper theory, one that can unify gravity with quantum mechanics. String theory offers one possible framework. Quantum gravity offers others. These approaches attempt to describe space-time as emerging from more fundamental building blocks: vibrating strings, quantum networks, discrete units of geometry. But so far, these ideas remain mathematical, elegant, powerful, and largely untested. We do not yet know what the interior of a real black hole is made of. We do not know whether singularities truly exist, or whether they dissolve into something more subtle when quantum effects are included. What we do know is this: black holes mark the boundary not just of space and time, but of understanding itself. They are places where our most successful theories collide and break. In that sense, black holes are not failures of science. They are its most honest mirrors. They show us exactly where our questions stop working. And that raises a final and unsettling thought. Are we asking what is inside a black hole, when the real mistake may be the question itself? Black holes are often imagined as cosmic destroyers, devourers of matter, erasers of meaning, endpoints where everything we know is torn apart and forgotten. But that picture may be wrong. A black hole is not a machine built to annihilate information. It is a test, a challenge posed by the universe to the limits of human understanding. Those three numbers that define a black hole do not tell a story of simplicity. They tell a story of compression, of how much reality can be hidden behind so little that we can observe. They mark the boundary between what nature allows us to measure and what it keeps beyond reach. Objects like TON 618 or Phoenix A are not anomalies to be feared. They are messages, early chapters in a much larger book that we have only just begun to read. What unsettles us most is not the darkness inside a black hole. It is the realization that our questions may still be too crude, that we may not yet know how to ask the right ones. The universe does not deceive us. It does not hide the truth behind tricks or illusions. It simply does not explain itself in the language we expect. Black holes sit at the intersection of gravity, quantum mechanics, space, time, and information. They expose the seams in our theories. They show us where certainty dissolves into possibility. And in doing so, they remind us of something profoundly human. The greatest discoveries are not found when we think we understand the universe. They appear when the universe forces us to admit that we do not. The black hole does not erase knowledge. It demands that we earn it.